Hello there and welcome back to the Sleep Science. Tonight you're floating at the very beginning of time, long before planets, before stars, before anything remotely Instagram-worthy. The whole universe is still hot, thick, and glowing. Basically a cosmic soup that would ruin even the best air fryer. You probably won't survive this place since breathing pure plasma is, let's just say, not on the human recommended activities list. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're at it, type in the comments where you're listening from and what time it is right now for you. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The universe, in these first few 100,000 years after the Big Bang, is mostly a blur of hydrogen and helium, swirling like fog that hasn't figured out what to do with itself yet. No planets, no trees, no cats to sit on your keyboard, just a darkening expanse, waiting for structure. The first few minutes after the Big Bang were actually a nuclear workshop, though not the kind you'd find in a modern laboratory. In that brief fiery span, the lightest elements, hydrogen, helium, and a whisper of lithium, were forged. It's a little like baking a cake where the oven shuts itself off after 5 minutes. You get the basics, but no icing, no sprinkles, nothing fancy. You drift through this young cosmos and feel the emptiness pressing in. No galaxies yet, just patches where matter ever so slightly clumps together, thanks to gravity's gentle tug. It's eerie, like standing in a stadium before the crowd arrives, when all you hear is your own footsteps. Historians of science still argue whether these earliest conditions were smooth or slightly bumpy, but without those cosmic wrinkles, nothing larger would ever have formed. There's a mainstream fact that anchors you here: the famous cosmic microwave background, a faint glow still bathing the universe today, is the fossilized afterglow of this early era. When astronomers mapped it in the 20th century, it was like suddenly finding baby photos of the cosmos. Imagine opening an old shoebox and finding a picture of your parents as infants, except the picture is 13.8 billion years old. And here's a quirky tidbit to chuckle at. Lithium, the same element found in phone batteries, was among those firstborn atoms. So, in a sense, the Big Bang gave us the future power supply for both Teslas and your cousin's perpetually overheating smartphone. You drift deeper into this early universe, and silence becomes its soundtrack. There are no stars yet to sparkle, no planets yet to anchor your gaze, just darkness and cooling gas. You notice how hydrogen atoms float like patient notes in a song that hasn't begun. Time itself feels sleepy, stretching across vastness with nothing to break the monotony. Now imagine those first atoms as seeds. Alone, they're humble, but together, given gravity and time, they'll bloom into everything you know. Oceans, forests, nervous systems, and that awkward IKEA bookshelf you spent an afternoon building. Without them, there would be no chemistry, no biology, no late-night pizza cravings. And if you let yourself lean into the strangeness, it's almost funny. Every single atom in your body once floated in this dark, element-poor era, anonymous and indistinguishable. Your oxygen, your carbon, your calcium. They weren't yet forged, but their raw ancestors drifted here, waiting for stellar furnaces to arrive. Historians still debate how long the universe stayed in this starless dark age before the first lights flickered on. Was it a few 100 million years or a bit longer? The numbers shift as new telescopes peer deeper into the past. But the gist remains. You're suspended in a hush that lasted longer than human history by orders of magnitude. It's tempting to think of this time as boring, but really it's the stage being set. Like the awkward silence before a concert starts when the musicians are just tuning instruments. Hydrogen is the violin string, helium the percussion, lithium the rare flute. The orchestra hasn't begun, but you can feel the anticipation. Your eyes, if you could call them that in this strange thought experiment, adjust to the velvet dark. You sense that gravity is slowly, stubbornly pulling, sculpting invisible shapes out of the bland fog. These are the first blueprints of galaxies, though right now they look like nothing. And maybe the most serene thought of all, you are not separate from this. You are stitched from the same hydrogen haze, connected not just in theory but atom by atom. The breath you'll one day take, the laugh you'll one day release, all of it traces back to this quiet, patient moment when the universe was waiting to spark. The atoms don't know yet what they will become. They don't know they'll fuel suns, build worlds, or one day structure the neurons that let you wonder about them. They just float, in silence, in an endless night that doesn't even have stars to pin on the sky. The silence deepens, but gravity has a way of ruining silence. Out in that still, hydrogen-rich sea, tiny density ripples, barely distinguishable, become footholds for collapse. You drift along as vast clouds of gas begin to thicken, pulled inward by the most patient of forces. Gravity doesn't shout, it whispers, tugging atom by atom, drawing them closer. Slowly, the universe is learning how to clump, like flour gathering into dough. As you watch, a faint shimmer hints at what's coming. Hydrogen atoms collide more often, and helium tags along like the quieter friend at the party. The clouds aren't uniform. Some regions collapse faster, tightening into dense knots. The sheer scale is absurd, whole clouds spanning light years across. But in this hush, they fold inward with the grace of dancers practicing a very, very slow spin. Here's your mainstream historical note. It was Sir Isaac Newton who first formalized the rules of gravity in the 17th century, giving humanity the mathematical lens to predict such collapses. He probably didn't imagine his equations applied to billion light-year scales, but his apple-falling insight turned out to be the skeleton key for understanding how entire stars are born. A quirky aside for you. Medieval scholars once believed stars might be holes poked in a cosmic curtain, allowing heavenly light to seep through. Imagine trying to apply that logic here. Instead of curtains, you'd need a bedsheet the size of the universe and a tailor with patience beyond belief. Now drifting inside one of these collapsing clouds, you sense the atmosphere changing. The pull inward generates pressure, and pressure builds heat. Hydrogen atoms, once lazily drifting, now move faster, jittery as though they've had too much coffee. You feel warmth seep through the imaginary skin of your perspective, though warmth here means millions of degrees, not cozy campfire heat. Scholars still argue whether the very first stars, called population III stars, formed easily or only after long delays. Did they need dark matter scaffolding to stabilize them, or could gravity alone handle the work? The debate lingers, because the evidence of those first stars has long since burned out, leaving behind only whispers in today's universe. As the cloud contracts further, you notice rotation creeping in. Nothing collapses perfectly straight. Even the tiniest spin magnifies as the cloud shrinks. Like a skater pulling arms inward, the spin accelerates. The forming star begins to gather a disk of material around its belly. That disk, in eons to come, will serve as raw clay for planets, moons, and perhaps the occasional asteroid that rudely interrupts dinosaur plans. In this cradle, pressure keeps climbing, and the core of the protostar glows faintly red. Not quite a star yet. Think of it as a teenager practicing stage lines in the mirror. But you can sense the inevitable. Hydrogen will not stay idle under this kind of heat. It wants to fuse, to join, to become something greater. The airless expanse outside the cloud remains cold and indifferent, but here, in the heart of collapse, a spark of destiny hums. You realize you're witnessing the blueprint of your own ancestry. Without this step, gravity coaxing atoms into tight neighborhoods, there would never be the chemical richness you're built from. You pause to consider the timescale. This collapse doesn't take days or even centuries. We're talking millions of years, drawn out in slow motion, yet perfectly inevitable. The same way you eventually cave into late-night snacks, clouds eventually cave into gravity. As the forming star tightens, jets of material burst outward along its poles. It's the universe's messy haircut, blasting extra gas away so the star can stabilize. These outflows carve into surrounding space, clearing the neighborhood, like a neighbor finally trimming their overgrown hedge. Inside, though, the heart is nearly ready. Hydrogen nuclei are packed so tightly they begin brushing shoulders, a prelude to fusion. The protostar trembles at the threshold, glowing brighter. You hover near, marveling at the inevitability of ignition. It's astonishing to think. All of this drama is happening without intention, without direction. Just gravity, pressure, and physics stacking dominoes. And yet, from these collapsing clouds, the entire cosmic story unfolds. Galaxies, worlds, you. The heat inside the contracting core sharpens until hydrogen nuclei can no longer resist one another. Pressure presses them so close that quantum tunneling, the strange loophole of physics, lets them merge. Suddenly, you're bathing in light not from outside but from deep within. The star has ignited. The first fusion sparks flare like whispers of fire catching on dry wood. Hydrogen atoms slam together, forming helium, and in the process they release energy in the form of light and heat. You feel that rush of photons bursting outward, fighting gravity's squeeze. For the first time, the universe isn't just dark and collapsing, it shines. Here's the historical anchor. In the 1920s, British astrophysicist Arthur Eddington proposed that stars shine because of nuclear fusion in their cores. At the time, the idea was radical, since no one knew how matter could release that much energy. Today it's mainstream, but back then, suggesting that stars were giant nuclear furnaces was like saying your toaster could power an entire city. And a quirky tidbit, in the early days of physics, some scientists thought stars might be powered by literal burning, like coal fires on a cosmic scale. Problem was, even a sun-sized coal ball would burn out in a few thousand years. So, unless the dinosaurs were ordering takeout under LED bulbs, that theory didn't hold. As the fusion continues, balance arrives. Gravity still tugs inward, but the outward push of energy from fusion stabilizes the star. The result? Equilibrium, a long-lasting truce. You hover, watching this newborn star finally relax into itself, like a candle finding its steady flame. Scholars still argue over exactly what those first fusion-powered stars looked like. Were they monstrously massive, hundreds of times heavier than our sun, or were some small and faint? The data is scarce, and the telescopes of today are still chasing shadows of those ancient beacons. The light from these stars cuts through the darkness of the cosmic dark ages. For the first time, photons travel freely across space, painting the void with their glow. Imagine being in a pitch-black theater when the curtain finally rises and stage lights snap on. Suddenly, the emptiness is full of texture. You lean closer and feel the warmth of hydrogen to helium alchemy. The star hums, not in sound but in steady radiance. It is a factory that will run for millions, maybe billions of years, turning simple hydrogen into more complex helium cores. A patient, relentless chef simmering the universe's first broth. Outside the star, the surrounding gas cloud responds. Radiation blows away leftover material, sculpting space into arcs and pillars. It's messy and magnificent, as if a toddler with a leaf blower were in charge of interstellar gardening. And now you realize, this moment is the beginning of chemistry beyond the Big Bang's plain menu. Helium wasn't new, some of it already existed. But here, stars are actively creating it in bulk, stockpiling fuel for the cosmic future. Every flicker, every sparkle you'll one day see in the night sky is a factory working overtime, reshaping hydrogen into helium. There's comfort in the rhythm. The universe doesn't rush. Stars form, settle, and shine on timescales that make human worries feel tiny. That assignment due tomorrow, a joke compared to a star calmly fusing for 10 billion years. You let the glow wrap around you. The once empty cosmos now hosts scattered islands of light, each one marking a furnace where hydrogen is being pressed into something new. The silence is no longer lonely. It's studded with the steady beat of stellar hearts. And the most astonishing thought drifts in as you float. Every single breath you will ever take depends on these early stars learning how to fuse. Without this gentle fire, there would be no oxygen, no carbon, no nitrogen. This is the universe's first chemistry lesson, and you are made of its homework. The star burns on, and with time, its core tells a new story. Hydrogen is plentiful, but like every party snack, it doesn't last forever. When the hydrogen in the core dwindles, fusion slows and gravity once again pushes inward. The star, refusing to simply vanish, finds another trick. It begins to fuse helium into heavier elements. You hover close enough to sense the transition. The core contracts and heats, enough for helium nuclei, 3 of them at a time, to smash together into carbon. This reaction is called the triple alpha process, and it's the first step toward complexity. Imagine 3 helium atoms linking arms like dancers forming a triangle, suddenly realizing they've become something entirely new. Here's your mainstream historical fact. In the 1950s, British astronomer Fred Hoyle argued that the universe's abundance of carbon meant this process had to be real. He even predicted a specific resonance, energy level in carbon that allowed the reaction to happen. Later experiments proved him right, saving barbecue grills, red blood cells, and chocolate cakes everywhere. Because without carbon, none of those exist. And a quirky tidbit, Hoyle, despite being a brilliant scientist, also championed the idea that life on Earth might have arrived via microbes hitchhiking on comets. The theory, panspermia, isn't mainstream, but it's fun to imagine cosmic spores floating through space like dandelion seeds. Back in the stellar core, after carbon comes oxygen, born when carbon fuses with helium. Neon follows, glowing faintly in your imagination like a sign outside a galactic diner. The star is layering its interior like a cosmic onion. Hydrogen on the outside, helium deeper in, then shells of carbon, oxygen, and neon forming as the furnace intensifies. Historians still argue whether all stars follow the same element-building ladder, or whether some skip rungs depending on their mass. The exact sequence remains an active debate, especially for the earliest stars that lived fast and left no corpses behind. You glide through the star's layers, noticing how each shell pulses with its own rhythm. In one zone, helium fuses. In another, carbon ignites. The star has become a multitasker, juggling multiple nuclear processes simultaneously. It's like a chef running 6 stoves at once, each with its own bubbling pot, somehow not burning the entire kitchen down. The beauty of it hits you. These are the ingredients of life being stockpiled. Carbon for your cells, oxygen for your breath, neon for, well, glowing pub signs much later. The star doesn't know it's doing you a favor, but every fusion step is laying the groundwork for your existence. Outwardly, the star swells, often into a red giant. Its outer layers balloon, turning it into a luminous lantern visible across galaxies. If you could stand near it, the scale would be absurd. The star's bloated skin might stretch out to where Earth's orbit is today. Not exactly ideal real estate. The atmosphere of this giant feels unstable, like being near someone juggling knives with one eye closed. Pulsations ripple through its surface, and stellar winds begin to blow off gas into space, spreading freshly minted atoms outward. Already, the universe is richer than it was 1 billion years ago. And you can't help but smile at the irony. Humanity fusses over recycling bins, while stars casually recycle entire elements across galaxies. No fuss, no lectures about separating plastics. Inside, though, the real marvel continues. Carbon and oxygen, two of the most essential atoms for life, are not Big Bang relics. They are children of stellar hearts, hammered together by pressure and fire. To inhale oxygen today is to inhale stardust, transformed long before Earth even existed. The star doesn't know it's forging your bones, your teeth, your laughter, your stubbornness. It just fuses tirelessly until the fuel runs out. You float in the glow of this process, aware that the atoms destined to be your cells are being written here, line by fiery line, into the cosmic script. The furnace hums on, but even stars have limits. Deep in the core, the sequence of fusion reactions keeps climbing the elemental ladder. Helium to carbon, carbon to oxygen, oxygen to neon, neon to magnesium, and on it goes. Each new step takes more heat, more pressure, more stubbornness from the star. You hover nearby, sensing the core hardening under this relentless alchemy. Eventually, the star arrives at a wall it cannot climb. That wall is iron. Iron is a paradox in the stellar cookbook. Fusing lighter elements releases energy, but iron does the opposite. Try to fuse it, and instead of liberating power, the reaction eats energy. It's like a vending machine that takes your coins and gives you nothing in return. Here's the historical fact. In the 20th century, nuclear physicists like Hans Bethe worked out the details of fusion and showed why iron is the cosmic dead end. This discovery was a turning point because it explained not just how stars live, but also why they must die in such spectacular fashion. And the quirky tidbit: ancient cultures prized iron from meteorites long before humans discovered smelting. Tutankhamun, the famous Egyptian boy king, was buried with a dagger forged from meteoritic iron, a literal blade from the stars. Humans, in their way, sensed that iron was already cosmic long before science explained it. Back inside the star, you feel the tension. Fusion has stalled at the core, no more energy to balance gravity. The star, once a well-organized multitasker, now trembles under its own weight. Outer shells still fuse lighter elements, but the center is a heavy, unyielding ball of iron. It grows denser by the moment, like the universe is tightening a knot it can't undo. Historians still argue over the fine details of how rapidly these final stages unfold. Some suggest the layering and collapse happen in just a few days, others in mere hours. Either way, compared to the millions of years of steady burning before, this is a sprint toward catastrophe. From your vantage, it feels eerie, like standing in a theater where the orchestra suddenly falls silent, and you know the crash of cymbals is coming. The star's outer layers rumble with instability, convulsions rippling outward, but the true drama is hidden deep inside, where iron gathers like an anchor pulling everything down. The balance between gravity and pressure, that long-standing truce, finally cracks. Gravity begins to win, dragging matter inward with unstoppable force. The core, no longer supported by fusion's fire, collapses. Temperatures and densities spike to unimaginable extremes, but iron refuses to yield its energy. The star is cornered. You linger for a breath, aware that this stalemate, fusion's dead end, will trigger one of the most violent events in the cosmos. All the elements that matter to you, beyond carbon and oxygen, are waiting behind this threshold. Without iron's stubbornness, there would be no explosions to scatter gold, uranium, or iodine into the void. The irony is deliciously cosmic. The same element that makes up skyscrapers, frying pans, and the hemoglobin in your blood is also the element that brings a star to its knees. Iron is both life-giver and executioner, both keystone and full stop. The star grows quieter, as if holding its breath. You feel the weight of inevitability pressing in. This is the calm before the thunderclap, the pause before the universe clears its throat and shouts across galaxies. The pause shatters. The iron core, no longer able to hold itself up, collapses inward at a speed so staggering your mind can't quite follow. In less than a second, a core the size of Earth shrinks down to something the size of a city. The outer layers don't get the memo in time. They crash inward too, slamming into the rebounding core with unimaginable force. The result is the cosmic equivalent of an orchestra hitting every instrument at once, a supernova. You drift back instinctively as the star erupts, its brilliance outshining an entire galaxy for days. Light, heat, and shockwaves blast outward. Space that was once quiet now roars with energy so intense it can strip electrons off atoms across interstellar distances. Here's the historical note. In 1054, astronomers in China, Japan, and the Middle East recorded a supernova so bright it was visible in daytime for weeks. Today, its remnant is the Crab Nebula, a tangled, glowing cloud still expanding almost 1,000 years later. Imagine walking outside at noon and seeing a new star, rivaling the sun. Medieval sky watchers must have felt the universe was cracking open. And for the quirky tidbit, in the 16th century, Tycho Brahe observed a supernova and stubbornly called it a new star. At the time, European scholars still believed the heavens were unchanging. Tycho's discovery was basically the universe saying, "Yeah, about that eternal perfection thing. Surprise." As you hover near the explosion, the violence feels both terrifying and beautiful. The shockwave tears through the star's outer layers, shredding them into glowing shrapnel. The energy is so great that new elements, heavier than iron, are forged in the chaos. Gold, silver, uranium, iodine, even the calcium that will one day form your bones, all hammered into existence in this fraction of a second. Historians of science still argue whether the majority of heavy elements come from supernovae alone, or if neutron-star collisions play the bigger role. The debate continues, but no one denies that supernovae are elemental factories, each blast enriching the galaxy like a cosmic piñata spilling treasures. The sensory experience is overwhelming. Radiation floods outward, not in a single burst but in waves, like the star is exhaling its last breath again and again. The debris glows with every color your imagination can paint: reds, blues, greens, each corresponding to different atoms excited into light. You drift through the aftermath, the expanding cloud curling into filaments, twisting into knots. Already, this material is spreading across light years, seeding space with the products of stellar death. In a few billion years, these atoms may condense into new stars, new planets, maybe new beings wondering how it all began. What strikes you most is the paradox. Destruction is creation. The star's death is violent, yes, but without it, the universe would remain stuck at helium, carbon, and oxygen. Your blood, your skeleton, your nervous system, all require this explosion. It's unsettling to think your very existence depends on explosions that could sterilize entire solar systems. The light of the supernova continues to blaze, but the core left behind has transformed. Sometimes it becomes a neutron star, a city-sized ball so dense that a teaspoon would weigh more than a mountain. Sometimes, if the collapsing core is massive enough, it becomes a black hole, swallowing even light itself. Either way, what remains is utterly alien, a reminder of just how far from ordinary physics you've drifted. You glance back at the shockwave still tearing outward, scattering stardust across the void. It's chaotic, yet strangely peaceful, like fireworks seen from a great distance, their danger replaced by beauty. The truth sinks in. You are watching the exact process that made you possible. Somewhere long ago, your calcium was forged in one such blast, your iron in another. Your body is a patchwork quilt of supernova debris, stitched together billions of years later into a person who can lie in bed and wonder about stars. The fireworks fade, but the story of the elements doesn't end with supernovae. Some ingredients of your body, especially the glittering metals we obsess over, come from an even stranger, rarer kind of cosmic collision. You float now into a darker patch of the galaxy, where two neutron stars are locked in a deadly dance. They orbit each other like two heavyweight wrestlers circling the ring, spiraling closer with each pass. Their mass bends space itself, sending ripples, gravitational waves, rippling across the universe. If you had superhuman ears tuned to space-time, you'd hear their orbit as a rising chirp, higher and higher, until the moment of impact. Here's the historical note. In 2017, scientists detected gravitational waves from a neutron star collision, and telescopes around the world caught the light from the aftermath. For the first time, humanity witnessed not just the crash but the gold-making fireworks it produced. Newspapers had headlines along the lines of "The universe just made bling." And a quirky tidbit. Some researchers estimate that a single neutron star merger can produce more gold than Earth's entire crust contains. If you could scoop up the ejecta, you'd have enough jewelry to make every rapper on the planet jealous, with plenty left for a golden statue of your dog. The collision comes suddenly. The two stars slam together, releasing more energy in seconds than the sun will emit in its entire lifetime. You're blinded, metaphorically of course, by a flash brighter than anything you've seen. Matter sprays outward, neutron-rich and unstable, quickly reorganizing itself into heavy elements: gold, platinum, uranium, lanthanum. All the exotic ingredients needed to spice up the cosmic recipe. Scholars still argue whether supernovae or neutron star mergers contribute more of these heavy elements to galaxies. Some say the universe's gold is mostly merger-born. Others argue supernovae still play a bigger role. The debate remains unsettled, shimmering like the very metals in question. You drift through the ejecta, and it feels like wading through glowing dust. Each mote is an atom freshly minted in violence. Some of them, gold and platinum, will one day adorn wedding rings and crown jewels. Others, like uranium, will be split in nuclear reactors to power cities. And still others, obscure names like europium and neodymium, will wind up in the magnets inside your headphones. The beauty of it is almost absurd. Out of destruction comes treasure. Humans may argue endlessly about the value of gold, but here you see its origin, not in markets or mines, but in a cosmic collision billions of years ago. That bracelet on someone's wrist is the fossilized memory of a neutron star smash. You pull back and watch the debris cloud expand, glowing faintly with radioactive heat. For weeks, maybe months, it will shine, a phenomenon astronomers call a kilonova. The light fades eventually, but the atoms remain, carried outward by galactic winds, mixing with the general fog of matter. And you realize with a sleepy smile that your own body contains atoms from both paths, the everyday supernova blasts and these rare neutron star mergers. Your skeleton, your bloodstream, your fingernails. They're a mixed inheritance of stellar catastrophes. It's oddly humbling. You are not just made of stardust. You are made of gold dust, uranium dust, rare earth dust. The jewelry store and the power plant, the crown and the circuit board, they all shimmer with echoes of neutron stars tearing each other apart. The dance is over now, the two stars gone, their atoms scattered. Silence returns, but it feels fuller, richer, because now the universe carries more kinds of matter than it did before. Somewhere, eventually, these atoms will cool, condense, and join new stars and worlds. Somewhere, one day, they'll even help spark the neurons that let you marvel at their journey. The galaxy now hums with leftovers. Everywhere you drift, you find trails of gas, dust, and atom-rich debris from countless stellar deaths. It's messy, but it's also productive. The universe is, at its core, a master recycler. Nothing is wasted for long. Clouds of gas darken against the starlight, dense with molecules and dust grains. These clouds are the interstellar medium, the recycling bins of the cosmos. Bits of carbon from one star, oxygen from another, calcium from yet another, all mingle together like ingredients tossed into a galactic stew. If you could hold a scoop of this dust, you'd have the future bones of planets in your palm. Here's your historical fact. In the 1930s, astronomer Lyman Spitzer argued that interstellar dust wasn't just random clutter, but played a vital role in forming stars and planets. His ideas, once controversial, laid the foundation for modern astrophysics. Without that dust, no planets would form, and you wouldn't have a comfy bed to listen from tonight. And the quirky tidbit: ancient Babylonians thought the Milky Way was made of milk spilled by a goddess. Honestly, compared to explaining interstellar dust clouds filled with silicates and carbon compounds, that version might sound more appetizing. As you drift deeper into one of these dark clouds, you notice the hush. The dust blocks starlight, creating cool, shaded pockets where molecules can stick together. It's in these quiet corners that chemistry begins to stretch its legs. Hydrogen atoms pair up into H2, forming the simplest molecule, while carbon and oxygen begin flirting, creating carbon monoxide and water. The galactic pantry is filling with basics. Scholars still argue over exactly how efficiently this recycling happens. Do supernovae inject more dust into the galaxy than they destroy? Does dust survive the violent radiation of young stars? These questions keep researchers busy, peering through telescopes at clouds millions of light years away. You can almost hear the process: grains of dust clinking together, atoms locking into new patterns. Silicates, iron oxides, carbon soot, tiny particles suspended in vast clouds. Each grain, no bigger than smoke, drifts for millions of years until gravity corrals it again. From your perspective, the clouds resemble cosmic weather systems, swirling and curling. In some regions, the dust is thick enough to birth stars anew. Elsewhere, it drifts, waiting its turn. The cycle is endless. Stars live, explode, scatter their ashes, and the galaxy gathers them up to begin again. It makes you think of a thrift shop. Nothing here is brand new, yet everything is useful. Your bones may contain calcium once coursing through a starfish on a world that no longer exists. The iron in your blood might have first sat in the crust of a long-dead planet, pulverized and recycled into new clouds. Cosmic reincarnation, atom by atom. And the visuals: dark tendrils of dust silhouetted against glowing nebulae, streaks of crimson and sapphire painted by ionized gases. It's like the galaxy hired a particularly flamboyant interior decorator. You float, bathed in those hues, soothed by the slow pulse of creation unfolding around you. The thought sneaks in: when you breathe in oxygen tomorrow, you'll be inhaling something with a rhizome older than Earth. Dust clouds prove that nothing ever truly disappears. It only transforms, waits, and returns in a new role. Here, in this recycling bin of the cosmos, you feel a quiet connection to everything. Every atom is a traveler, carrying stories from long-dead stars, waiting to join the next adventure. You realize that even when you're gone, your atoms will scatter and cycle too, ready to join the next chapter of the galactic script. The recycled clouds swirl, and from one of them, a particularly familiar star begins to glow. You drift closer, and the scene feels oddly personal. This is no ordinary star. It is your star, the Sun, born about 4.6 billion years ago from one of these enriched, dusty nebulae. The very cloud you've been floating through collapses, flattening into a spinning disk. At the center, the Sun ignites, and around it, leftover dust and gas swirl into a broad cosmic platter. Here's your historical anchor. In the mid-18th century, philosopher Immanuel Kant and mathematician Pierre-Simon Laplace both proposed a nebular hypothesis, the idea that the Sun and planets formed from a rotating disk of gas. Their guesses, made centuries before telescopes could confirm such disks, turned out remarkably close to what modern astronomy sees today. And here's the quirky tidbit. In the 1960s, astronomers thought the Sun might be unusual, a cosmic loner formed in isolation. Now we know that most stars are born in clusters. Our Sun probably had stellar siblings, scattered across the Milky Way. Somewhere out there, far beyond what you can see, other stars are carrying the same family stardust you carry in your cells. The disk around the newborn Sun is chaotic. Gas whips, dust grains collide, icy clumps drift inward. You hover above it like a bird over an unfinished nest. Hydrogen and helium dominate the outer regions, while heavier elements, carbon, oxygen, silicon, iron, settle nearer to the center. These are the ingredients of planets waiting to be baked. Scholars still argue over whether a nearby supernova shockwave triggered the Sun's birth. Certain isotopes in meteorites hint at freshly minted atoms from a dying star mixed into the solar nebula. If true, then our Sun was nudged into existence by a neighbor's dramatic exit, a cosmic baton pass of life-giving matter. The light of the newborn Sun is softer than today's familiar blaze. It's still stabilizing, still shaking off the chaos of formation. Around it, the protoplanetary disk spins like a slow-motion carousel, shimmering with dust grains glowing in reflected light. Some clumps grow larger, sticking together through electrostatic attraction and then gravity, becoming kilometer-sized planetesimals, the first building blocks of Earth and her siblings. You realize that this is the inheritance of everything you've seen so far. Hydrogen from the Big Bang, carbon and oxygen from ancient giants, gold and uranium from neutron star collisions, calcium and iron from supernovae. The Sun and its disk are a hand-me-down wardrobe stitched from billions of years of stellar recycling. The atmosphere here is busy but oddly soothing. Dust spirals inward, ice migrates outward, magnetic fields dance. You can almost hear it, a low white noise hum of particles colliding, like grains of sand tumbling in a river. From this disk, every planet, moon, asteroid, and comet in the solar system will emerge. And tucked inside them will be the atoms that will one day make oceans, mountains, forests, and you. It feels almost intimate, as though you're paging through the photo album of your own conception. The Sun, glowing steadily now, holds the system together. Its warmth and gravity are the constants against which everything else will take shape. You can imagine its light falling across the swirling disk, turning dust motes into golden specks, cosmic confetti at the birth of a system. And the thought drifts in, sleepy but profound. You are not just made of stardust, you are made of family stardust. Every atom in you belongs to this neighborhood of the galaxy, this particular star and its siblings. Your body is the autobiography of a cloud that chose to collapse, spin, and ignite. The disk spins, thins, and clumps. Over millions of years, the loose grains of dust collide and stick, first like flour gathering into dough, then like pebbles fusing into boulders. Gravity lends a hand, pulling these objects together until they grow large enough to bully smaller ones into joining. You watch as the chaos of the protoplanetary disk gradually organizes itself into a cast of rocky and gaseous worlds. Near the sun, where it's too hot for ice to survive, rocky planets begin to take shape. Mercury, Venus, Earth, and Mars, the quartet that will someday be called the terrestrial planets, are forged here from silicates, iron, and nickel. Farther out in colder zones, gas and ice giants form, Jupiter and Saturn swelling into behemoths that hoard hydrogen and helium. Beyond them, Uranus and Neptune collect ices of water, methane, and ammonia. Here's the historical fact. In the 17th century, Johannes Kepler puzzled out that planets move in ellipses around the sun. His laws of planetary motion, derived from careful data, gave later scientists the tools to understand how these early planetary embryos would settle into orderly orbits. And a quirky tidbit: some ancient Greek philosophers thought planets were divine beings moving under their own will. Imagine trying to explain Saturn's rings to someone convinced the planet just felt like accessorizing. As you float above this early solar system, the scene is anything but peaceful. Planetesimals crash into each other with bone-rattling violence, releasing plumes of molten rock into space. Some grow into planets, others are smashed to rubble. It's a cosmic demolition derby. Only the survivors earn the right to orbit stably. Historians still argue over the late heavy bombardment, a theorized period when leftover debris battered the young planets, carving craters still visible today on the moon. Was it a sudden spike of impacts or just a slow decline stretched across eons? The debate rumbles on, written into the pockmarked surfaces of rocky worlds. You zoom in on Earth's early form. It glows with molten seas, its surface churned by impacts. One collision is especially dramatic. A Mars-sized object slams into the proto-Earth, blasting debris that eventually coalesces into the moon. You can almost feel the heat, the shock, the slow dance of gravity knitting fragments into a companion that will shape tides and stabilize Earth's tilt for billions of years. Elsewhere, the giant planets flex their muscles. Jupiter's immense gravity slings comets and asteroids like a cosmic goalie blocking shots, but it also destabilizes orbits, scattering debris across the system. Some of those icy wanderers will one day bring water to Earth, sprinkling oceans onto a parched surface. The sensory impression here is wild. Molten rock glowing orange, clouds of ash curling skyward, shockwaves echoing across a still-forming crust. And yet, amid the violence, you sense purpose. Every collision, every accretion, every orbit is writing the foundation for a habitable world. The dust thins as planets sweep up the leftovers, their orbits clearing paths through the chaos. The sun shines more steadily now, bathing its children in light. Earth cools, hard crust forms, and volcanoes belch out gases that will one day thicken into an atmosphere. It's not exactly a vacation spot. Lava oceans, toxic air, frequent asteroid impacts. But it is, improbably, the birthplace of everything you'll ever know. And as you drift, you feel the intimacy of it. The iron forged in dead stars now sinks into Earth's core, generating a magnetic field that will shield life from solar storms. The oxygen and silicon form crustal rocks, carbon weights, tucked in the mantle and atmosphere, ready to fuel the chemistry of life. Every atom here has a pedigree stretching back through explosions and collisions, patiently waiting to be arranged into something new. You can't help but chuckle at the cosmic recycling program. Billions of years of star deaths, just so that atoms could clump into a world where beings eventually invent Wi-Fi and burritos. Earth cools, but only in a relative sense. You hover above a young world glowing with energy, its crust cracking, oceans steaming, and volcanoes roaring like the planet has a serious anger problem. Yet amid all this fire and fury, the recipe for life is being stirred. Volcanoes belch gases, carbon dioxide, nitrogen, water vapor, forming a primitive atmosphere. Lightning flashes through the clouds, sparking chemical reactions. Asteroids deliver more water and exotic molecules, splattering the surface like careless chefs tossing in surprise ingredients. The air is unbreathable to you, but to chemistry, it's paradise. Here's your historical anchor. In the 1950s, scientists Stanley Miller and Harold Urey ran a famous experiment, zapping a mixture of simple gases with electric sparks. Within days, amino acids, the building blocks of proteins, appeared in their flask. It was the first laboratory hint that Earth's early conditions could indeed cook up life's recipe. And here's the quirky tidbit. One hypothesis suggests that Earth's first sunscreen was crocodile dung. Not for humans, of course, we're still millions of years away, but for early organisms shielding themselves from harsh ultraviolet light. Life, apparently, doesn't start with glamour. As you drift closer, you feel the pulse of tectonic forces beneath the crust. Vast oceans boil, cool, and settle into basins. Currents churn minerals, carrying them into shallow pools. The air smells sharp, sulfur and methane, not exactly spot A aromas. But every storm, every eruption, every lightning bolt is an ingredient in the stew of possibilities. Historians still argue whether life began in shallow ponds, deep-sea hydrothermal vents, or even within icy comets that melted after impact. No one agrees on the location of the cosmic kitchen, but the consensus is clear. Earth had the right ingredients, the right energy, and plenty of time. You glide into the ocean, watching vents belch mineral-rich fluids into the water. Around them, minerals crystallize into chimneys, their surfaces bristling with energy gradients. Tiny pockets form natural reaction chambers where molecules can mingle. You imagine them whispering to one another, trying out new arrangements. Some will dissolve, others will persist. A few will become the foundation of something astonishing. On land, shallow pools dry and refill, concentrating molecules like reducing a sauce on a stove. Layers of clay act like tiny templates, guiding chemicals to stack into chains. You realize how patient this process must be. Millions of years of trial and error before the first stable, self-replicating molecule clicks into place. It's humbling. The atoms forged in stars, scattered by explosions, gathered into Earth, are now arranging into molecules that can copy themselves. From stardust to soup to life, all in the blink of cosmic time. The sensory details overwhelm you. The hiss of steam vents, the sizzle of lightning, the gurgle of hot springs, the taste of iron and salt in the air. The planet feels alive long before biology has even begun. And the irony settles in. The same volcanic violence that would terrify a modern traveler is exactly what made life possible. Without the chaos, there would be no calm, no oceans to swim in, no forests to hike, no cozy beds to sink into tonight. You float above the surface again and let the scale wash over you. Earth is a cauldron, and inside it, atoms are learning new tricks. Somewhere in a droplet, a chain of molecules will soon stumble into the ability to copy itself. The recipe isn't perfect yet, but the oven is hot, the ingredients are fresh, and the meal is already on its way to being served. The world steadies, its crust firming and oceans stretching wide. You hover above the surface, sensing the quiet magic of carbon, the element that decides to play by its own rules. If atoms had personalities, carbon would be the extrovert at the party, linking arms with almost everyone in sight, building chains, rings, and lattices like it can't help but mingle. In Earth's oceans and mudflats, carbon atoms begin assembling into increasingly complex shapes. Long chains twist into spirals, rings interlock, sheets fold over like origami. Some arrangements turn unstable and collapse, but others endure. You imagine them as Lego bricks, infinitely versatile, snapping together into structures limited only by time and creativity. Here's your historical anchor. In the 19th century, Friedrich Wörthler accidentally synthesized urea, an organic compound from inorganic materials. It shattered the belief that life chemicals could only be made inside living things. Carbon, it turned out, wasn't picky. It would build with anyone, anywhere, even in a flask on a laboratory bench. And for the quirky tidbit, carbon doesn't just make proteins and sugars. It also makes diamonds, the hardest natural substance, and graphite, the soft, greasy stuff in pencils. Imagine proposing to someone with an engagement ring made of pencil lead. Technically still carbon, but you might not get a yes. Back in the primordial soup, carbon bonds with hydrogen, oxygen, and nitrogen, producing amino acids, sugars, fatty acids. These molecules are like an alphabet slowly assembling letters into words. Some arrange into membranes that form bubbles, trapping other molecules inside. Others fold into catalysts, encouraging faster reactions. You can feel the momentum building. Scholars still argue whether RNA, capable of both storing information and catalyzing reactions, was the true pioneer of life. Was it RNA world first, or did proteins and membranes evolve alongside? The debate lingers, but everyone agrees carbon was the scaffolding that made any of it possible. You drift closer to a tide pool. Droplets shimmer as they dry in the sun, concentrating molecules into thicker soups. Carbon chains line up and stick, stacking into primitive structures. The sight is unassuming, almost dull, nothing glowing, nothing exploding, but the stakes are enormous. This is the quiet rehearsal for biology itself. Carbon's versatility means no two pools are alike. In one, chains loop into rings that may later become sugars. In another, fatty molecules stretch into membranes that will someday resemble the skin of cells. Carbon doesn't just connect atoms, it connects futures, seeding possibilities across the landscape. The sensory impression is subtle but powerful. The air smells faintly metallic, the water briny and thick, the mud warm under a prehistoric sun. It's not romantic, but it's fertile, a chemistry set written on the world's surface. And you realize, every protein in your body, every sugar fueling your brain, every stretch of DNA spelling out your existence depends on this moment when carbon proved it could do anything. Your muscles flex, your neurons fire, your bones grow, all because carbon decided long ago to be the friendliest atom at the party. The irony is sweet. Humans write poems about love and longing, but the deepest romance might be carbon's endless willingness to bond. It doesn't get jealous, doesn't quit, doesn't hold grudges. It just keeps connecting over and over until something extraordinary arises. You let the realization sink in. Carbon isn't just part of you, it is the architect of you. The latticework of your bones, the double helix of your DNA, the flickering signals in your brain, all carbon's handiwork. Every thought you've ever had is built on a framework that began here, in the chemistry of a restless young Earth. The ocean's calm, the skies thin, and a breath of possibility drifts across Earth's surface. You hover above a world where oxygen, one of the universe's most restless gifts, is quietly taking its place in the story. Forged in the bellies of massive stars and scattered by supernovae, oxygen atoms now slip into water, rock, and air, waiting for a role far greater than anyone could guess. In the shallows, cyanobacteria emerge, tiny architects with an astonishing talent: photosynthesis. They capture sunlight, split water, and release oxygen as a waste product. At first, it seems harmless, just bubbles fizzing into the seas. But those bubbles add up, seeping into the oceans, then the atmosphere, slowly changing the chemistry of the entire planet. Here's your historical anchor. Geologists call this shift the Great Oxidation Event, around 2.4 billion years ago. Evidence lies in banded iron formations, ancient layers of rock streaked with rust-red iron oxides. They mark the moment when oxygen first began binding with iron in Earth's seas, painting the planet with star-forged breath. And a quirky tidbit: oxygen is so reactive that if plants stopped producing it, Earth's atmosphere would lose its breathable supply in just a few thousand years. Basically, you owe every lungful of air to a planetary forest you didn't even plant. You drift into the ocean, watching iron particles sink in crimson clouds, locking oxygen into stone. The water tastes metallic, harsh, but also alive. It's the flavor of transformation. Oxygen doesn't sit quietly. It rearranges bonds, reshapes. With it, molecules like sugars and proteins find new ways to release energy. Life gets a boost of power, like switching from candlelight to electricity. Scholars still argue whether oxygen was a blessing or a curse for early organisms. Many anaerobic microbes, perfectly happy without it, perished in the rising tide. To them, oxygen was poison. Yet for others, it was opportunity, fuel for more complex metabolisms, the first step toward multicellular life. You surface and feel the shift. The sky grows clearer, tinged with faint blues. The air is thin, still far from today's mix, but breathable futures are on the way. Oxygen not only fills the lungs of creatures yet to evolve, it shapes climates, oceans, even the ozone layer that shields life from ultraviolet rays. You breathe in, and the sensation is almost intimate. Each molecule of oxygen entering your body carries a pedigree, forged in a star, released in a supernova, recycled through dust clouds, folded into earth, and now exhaled by a tree or a bacterium. Every breath is a chain of ancestry longer than history itself. And the humor of it: you walk around casually inhaling stellar debris, exhaling it again without ceremony. The air you sigh out during a boring meeting might contain atoms once inhaled by a dinosaur, or even by Cleopatra. Oxygen has no loyalty. It just keeps circulating, endlessly recycled. The more you dwell on it, the more sacred it feels. You are breathing the universe's leftovers, transformed into the very gas that keeps your cells alive. Oxygen isn't just part of life. It is the rhythm of life, the invisible bridge between stars and lungs. You let your shoulders drop, sinking into the thought. With every inhale, you're rejoining the story of stars. With every exhale, you're adding your own line. Breathing is not just survival. It's participation in a cycle that began billions of years before you and will continue long after. Your breath steadies and you drift deeper into yourself. Bones, teeth, skeleton, structures built not from air or water but from heavier stardust. Calcium and phosphorus, two atoms forged in the violence of dying stars, now locked together to make the framework that carries you upright. Without them, you'd be more jellyfish than human. In the stellar factories you visited earlier, calcium was born when carbon and oxygen fused under intense heat. Phosphorus is rarer. Its origin still debated, but most scientists agree it emerged in supernovae, scattered into the galaxy like precious seasoning sprinkled across a dish. Both elements, gathered into Earth, settled into rocks, seas, and eventually cells, waiting for life to claim them. Here's your historical anchor. In the 18th century, chemist Hennig Brand isolated phosphorus by boiling vast amounts of urine. He was searching for gold, but instead he discovered a substance that glowed eerily in the dark. Imagine his disappointment and his horror when the neighbors asked why his lab smelled like an unwashed latrine. And for the quirky tidbit, the word phosphorus literally means light bearer. Ancient texts even used it as a poetic name for the planet Venus, the morning star. So every time you wiggle your toes or smile with your teeth, you're moving with the glow of an old celestial metaphor. You slip into the skeleton of your imagined body, feeling calcium's firmness. These atoms, pressed into lattices of hydroxyapatite, create the strength of your bones. Phosphorus links into DNA, forming the backbone of the double helix, carrying instructions from one cell to the next. Without phosphorus, the script of life would be illegible. Scholars still argue over how phosphorus first became bioavailable. It tends to lock itself up in minerals, insoluble and stubborn. Some say lightning or meteorite impacts helped free it into usable forms. Others propose that acidic volcanic pools dissolved it into solution. The truth may be a mix, another reminder that life's recipe had many chefs. You run a hand, metaphorical though it is, over the bone of your forearm. Hard, white, reliable. It feels less like material and more like legacy. Calcium from ancient stars, phosphorus from stellar deaths, now woven into the architecture of your body. The sensory details are subtle but profound. The click of teeth when you bite into food, the dull thud of feet striking the ground, the sharp snap of a bone breaking, and the miracle of it knitting itself back together. All of these depend on atoms born in supernova fire. And here's the joke the universe seems to play. You think of yourself as an individual, but your skeleton is a museum. Each bone carries atoms billions of years old, older than Earth itself, marching around as though they belong to you. The more you linger, the more reverent it feels. Your bones are not just structure, they are history books. Calcium and phosphorus didn't just choose you. They were recycled countless times before. In the teeth of trilobites, the shells of ammonites, the jaws of dinosaurs. Every fossil ever found is part of your ancestry, atom by atom. You stretch out, feeling the sturdiness of starlight hardened into bone. There's a strange comfort in knowing that when your story ends, those atoms won't. They'll crumble back into the soil, drift into rivers, maybe cycle into another skeleton someday. Bones are temporary blueprints drawn with eternal ink. Your gaze shifts inward into the steady thrum of your chest. Blood flows dark and rich, carrying oxygen to every cell. Its color deep crimson comes from iron, that stubborn element you saw halt fusion in stars. Here, though, iron is not an obstacle, it's a gift. Without it, you wouldn't survive a single breath. Each molecule of hemoglobin in your blood holds iron atoms at its core. Those atoms clasp oxygen, ferrying it from lungs to tissues. Imagine tiny star-forged chauffeurs, tirelessly shuttling molecules of breath through endless microscopic highways. Every thought, every twitch of muscle, every lazy sigh while lying in bed depends on their work. Here's your historical anchor. In the mid-19th century, physiologist Felix Hopsaler isolated hemoglobin and discovered its iron content. He realized that the very metal used to forge swords and railways was also flowing in our veins. Humanity learned that the same element shaping civilizations was also shaping every heartbeat. And a quirky tidbit: some squid and octopuses use copper instead of iron in their blood, giving it a bluish tint. So if you ever meet an alien with blue blood, don't panic. It might just be a fancy cephalopod with better underwater camouflage. Back in the star's death throes, iron was the doom of fusion. But here, inside you, it is the enabler of life. Every oxygen molecule you inhaled in Section 13 is now clasped by iron and released where energy is needed. Without it, your cells would starve, and your brain would fizzle out in seconds. Scholars still argue over how much of Earth's iron came from the planet's original formation versus later bombardments by iron-rich meteorites. Some geologists suggest the iron in your blood may have literally fallen from the sky billions of years ago. A cosmic delivery service, long before FedEx. You picture iron atoms nestled inside hemoglobin, shifting shape as they grab oxygen, then letting go when tissues call. It's a delicate dance, repeated millions of times every second in your body. The faint metallic taste of blood when you bite your lip is a reminder of this chemistry, stars lingering on your tongue. The sensory details intensify as you imagine blood flowing. The warm pulse in your wrists, the soft throb in your temples, the surge after climbing stairs. Every beat is powered by iron's readiness to bond and release, bond and release. You feel your body as a river of stardust in constant circulation. And the irony isn't lost on you. Iron once destroyed a star by refusing to yield energy. Now it sustains you by yielding oxygen with perfect precision. The same atom that collapsed suns now lets you climb mountains, dance, laugh, and yawn. You let the realization settle. With each heartbeat, you're reminded that stars didn't just scatter atoms randomly. They gifted the precise elements needed for circulation, breath, and thought. Iron is not an accessory. It is the bloodstream's anchor, tying you directly to supernova fire. And you can't help but chuckle softly. You might brag about having iron will, but in truth, you're not just metaphorically strong. You literally have iron in your veins, star metal pumping quietly every moment of your life. You listen closer, beyond bones and blood, and notice the smaller notes in the symphony of your body. Not everything inside you is carbon, oxygen, or iron. Trace elements, tiny but essential, spark functions you rarely think about. Without them, life would stall. Take iodine. You don't need much, but without it, your thyroid gland can't regulate metabolism. Every beat of sweat, every flicker of warmth in your body depends on this starlit atom. Then there's copper, conducting signals in enzymes, helping iron do its job with blood. Zinc, meanwhile, steadies proteins and bolsters your immune system. Each is a backstage technician keeping the show running smoothly. Here's your historical anchor. In 1811, French chemist Bernard Courtois discovered iodine by accident while processing seaweed ash. He noticed purple vapor rising and realized it was something new. From seaweed to starlight, this humble atom became a medicine still used today. And a quirky tidbit: the Victorians once put copper salts in food to make vegetables look greener. It worked, but it also poisoned people. Proof that not every Stardust recipe should end up on the dinner table. You drift into your own cells, shrinking until enzymes look like bustling machines. Zinc sits at the core of some, copper glows in others. Each atom holds a role out of proportion to its size. You realize that without these subtle players, the grander elements, carbon, oxygen, calcium, would fumble. It's the difference between an orchestra with violins and trumpets but no triangle or flute. The music would feel hollow. Scholars still argue where many of these trace elements originated. Did zinc come mostly from supernovae or from neutron star mergers? Was copper forged predominantly in giant stars or in more exotic explosions? The cosmic recipe card is still smudged, and researchers continue to puzzle it out. The sensory impression is delicate. You imagine tasting salt, not just sodium chloride, but a swirl of trace minerals. You feel the faint buzz of metabolism running smoothly because iodine atoms whisper to hormones. It's a reminder that sometimes the smallest details hold the most profound power. You smile at the thought. Humans are often dazzled by gold and silver, but your body would collapse without these less glamorous atoms. Forget jewelry, copper and zinc are in your enzymes, literally running the machinery of your cells. And there's humor here too. You probably never thank the iodine in your table salt when you feel energetic, or the zinc when your immune system fights off a cold. These atoms work thanklessly, unsung heroes of biology, Stardust with a quiet job description. The longer you linger, the more it feels like your body is a museum of cosmic relics, not just the obvious elements but the rarest whispers of stellar violence. Each atom, iodine, copper, zinc, is a signature from some long-vanished event tucked into your fingernails, your glands, your hair. You exhale and let it sink in. Your body is not only a tapestry of the common elements, but also an archive of rare stellar fireworks. You are, quite literally, carrying a periodic table inside you, stars stitched into flesh down to the tiniest trace. You float inward again, past the major elements and even past the traces that quietly keep you alive. There's something stranger hiding in your atoms, odd isotopes, the rare versions of elements that carry extra neutrons or decay in curious ways. They're like the eccentric cousins at a family reunion, not as common, not always stable, but unforgettable once you notice them. Some isotopes are fleeting. Aluminum-26, for example, decays with a half-life of about 700,000 years, short by cosmic standards. Yet traces of it appear in meteorites, hinting that a nearby supernova seeded the solar nebula right before Earth's birth. Its heat may have helped melt early planetesimals, shaping the worlds before they were even fully formed. Here's your historical anchor. In the mid-20th century, geochemists began studying isotopic ratios in rocks, realizing they were cosmic timestamps. Oxygen-18 versus oxygen-16 in ice cores, for instance, records ancient climate shifts. Suddenly, isotopes weren't just quirks, they were history books written in atomic script. And for the quirky tidbit, bananas are naturally radioactive because they contain potassium-40, a long-lived isotope. Don't panic, your snack won't turn you into the Hulk. You'd have to eat millions at once for it to matter, though that might earn you a world record for least enjoyable potassium overdose. As you drift inside the idea of isotopes, the sensory impression is subtle. Some atoms feel steady, grounded. Others hum faintly, unstable as though ticking down to transformation. You sense the quiet drama of decay, a neutron flipping into a proton, a whisper of energy released. These micro-events, multiplied across eons, shape everything from planet formation to medical imaging machines. Scholars still argue about the precise stellar events that seeded our system with these short-lived isotopes. Was it a single supernova detonating near the newborn sun? Or did winds from massive stars sprinkle them in gradually? The evidence is debated like a mystery novel missing its final chapter. You picture Earth forming amid this radioactive haze, isotopes heating its interior from the start. And thorium-232, both with half-lives measured in billions of years, still simmer beneath your feet today. They generate heat that keeps Earth's core molten, driving plate tectonics and, indirectly, earthquakes and volcanoes. The restless crust owes much of its motion to radioactive stardust. Inside your own body, isotopes tag along quietly. Carbon-14, produced in the atmosphere by cosmic rays, cycles through food into your tissues. If you vanish tomorrow, archaeologists in a distant future could date your remains by watching how much of it has decayed. You are, in a sense, a walking atomic clock, calibrated by the sky. The irony of it sinks in. Isotopes are both fragile and essential. They crumble over time, yet their very instability drives heat, powers medicine, and records history. You carry them without noticing, yet without them, Earth might have frozen solid long before life could bloom. You exhale slowly, amused at the thought that even your banana breakfast, your skeleton, and your very planet whisper with radioactivity. It's not dangerous here. It's just the afterglow of stellar events, ticking softly inside every atom. Stardust doesn't just shine, it keeps time. You pull back now, widening your gaze, and instead of zooming into single atoms or isotopes, you look at the whole. Your body becomes a constellation of elements, percentages and proportions echoing the cosmos itself. Oxygen makes up most of you, followed by carbon, hydrogen, and nitrogen. Sprinkled through are calcium, phosphorus, potassium, sulfur, and all the tiny trace elements. Add them together, and you're basically a walking star map. Here's the historical anchor. In 1957, a landmark paper by Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle, nicknamed B2FH, laid out the theory of stellar nucleosynthesis. They showed how stars build the elements, matching cosmic abundance charts to human chemistry. It was the scientific mic drop that proved the periodic table in your body really is a record of stellar history. And a quirky tidbit, if you boil down the math, about 93% of the atoms in your body are stardust. The other 7%, hydrogen born in the Big Bang itself, which means you're not only star-forged, you're partly Big Bang vintage, a limited edition cosmic blend. You float within your body, but it no longer feels like you. It feels like a census of elements, an inventory of cosmic inheritance. The percentages line up eerily well with what astronomers measure in the galaxy. Oxygen abundant, carbon versatile, iron steady but sparse, gold rare. You aren't just in the universe. You are statistically indistinguishable from it. Scholars still argue about the philosophical weight of this. Does being made of stars change how we view ourselves? Or is it just a scientific curiosity, no more profound than saying you share 60% of your DNA with a banana? The debate runs through classrooms and coffee shops alike, but the awe remains the same. You picture charts of stellar abundances, the spikes where oxygen and carbon dominate, the dips where rarer elements whisper. Then you overlay them on a chart of human body composition. The resonance is uncanny, as though evolution was simply following the script already written in stellar cores. The sensory detail is mathematical, yet strangely warm. Numbers float like constellations. 65% oxygen, 18% carbon, 10% hydrogen, 3% nitrogen, 1.5% calcium. You see them glowing above your skin like tattoos of cosmic statistics. It feels less clinical and more like a lullaby sung in percentages. And the humor is gentle. Imagine a nutrition label for yourself. Ingredients: 93% recycled stardust, 7% original Big Bang hydrogen. May contain traces of gold, copper, and zinc. Daily value of awe: 100%. You drift in this realization, peaceful and oddly proud. You are not merely related to stars, you are calibrated to them. Your chemistry is their chemistry. Your story is their story. Even the hydrogen in your cells has been drifting since the dawn of time, waiting to be poured into the mold of your body. It's humbling and thrilling at once, to look at yourself and see not vanity or imperfection but an echo of cosmic abundance. You are the galaxy rehearsed and performed in miniature. You are, in every sense, a star map walking on two legs. You linger in that awareness, floating in the overlap between science and meaning. The facts are clear enough. Your atoms were forged in stars, scattered by explosions, gathered into Earth and woven into you. But what does it mean to carry the cosmos in your skin and bones? That question has haunted philosophers for centuries. Here's your historical anchor. In the 4th century BCE, Greek philosopher Democritus proposed that everything is made of indivisible particles called atomos. He couldn't prove it, but the intuition was uncanny. 2,000 years later, science confirmed his hunch. Imagine how smug he'd be if he could see a modern periodic table. And a quirky tidbit. In the 20th century, surrealist artist Salvador Dali painted Galatea of the Spheres, depicting his wife's portrait broken into floating atomic orbs. Dali claimed he was inspired by the discovery of atomic structure, blending art and physics in a way only Dali could. He saw beauty where most saw math. Back in your drifting meditation, you sense the tension. To some thinkers, the fact that humans are stardust is the ultimate grounding, proof that we are natural, not separate children of physics. To others, it's spiritual, a reminder of unity with the universe, a spark of cosmic poetry hidden in chemistry. Scholars still argue about where the line lies. Does science erase mystery or does it deepen it? When you learn that your blood's iron once destroyed a star, is that less magical or infinitely more so? The debate is ongoing, woven into lectures, poems, and late-night dorm conversations. You drift through images of thinkers wrestling with the question. Carl Sagan famously whispered that we are made of star stuff, blending science with awe. Meanwhile, skeptics roll their eyes, reminding us that atoms don't care about meaning. And yet, here you are, feeling meaning anyway, stirred by the same atoms that don't even know you exist. The sensory impression shifts into reflection. You picture yourself walking through a forest, air rich with oxygen from trees. Each breath ties you to photosynthesis, which ties back to ancient stars. You hold a stone, dense with calcium and silicon, and feel its weight as the residue of stellar furnaces. You touch your own skin, knowing the carbon beneath it once flared in a red giant's core. Every gesture becomes a ritual of connection. And humor sneaks in, too. Imagine telling someone at a party, "Nice to meet you, fellow bundle of exploded star debris." Not exactly a smooth pickup line, but technically accurate. The more you lean into it, the more profound it becomes. You are not an outsider gazing at the cosmos. You are the cosmos, aware of itself. Every stargazer is the universe reflecting on its own past. Every question you ask about where you came from is really an atom asking about its own journey. You close your eyes and feel the weight of it. Meaning, after all, is something humans can't help but create. If stars forge the atoms in you, maybe your thoughts are just the universe's way of whispering back to itself, "I remember." You drift forward, past philosophy, past reflection, into the quiet certainty of what comes next. The atoms in you are not done. They've traveled for billions of years, and they will travel for billions more. You are only a temporary chapter in their infinite story. One day, your atoms will scatter again. Some will return to the soil, feeding trees and flowers. Some will wash into rivers, drift through oceans, or ride winds into the sky. Others may be carried far beyond Earth, locked in rocks that leave the planet as meteorites or dust kicked up by impacts. Eventually, whether in centuries or eons, every atom in you will leave its current arrangement behind. Here's your historical anchor. Astronomer Cecilia Payne in the 1920s revolutionized astrophysics by demonstrating that stars are composed mostly of hydrogen and helium. Her insight revealed not only what stars are but also what they recycle. She saw the cycle clearly. Stars, matter, and life endlessly exchanging roles. And a quirky tidbit: the Voyager spacecraft, launched in the 1970s, carry golden records etched with sounds and music from Earth. Those spacecraft and the atoms within them may drift between stars for billions of years. It's cosmic irony. While your atoms will scatter naturally, we also launched pieces of ourselves deliberately into the void. You picture your atom's future. Perhaps the calcium from your bones will one day solidify in the shell of an alien creature on a distant ocean world. Perhaps the carbon in your skin will fuse into graphite within Earth's crust, only to resurface in volcanic eruptions millions of years later. Perhaps the iron in your blood will drift into the heart of a star yet unborn, once again playing its paradoxical role in stellar life and death. Scholars still argue about the universe's ultimate fate. Will it expand forever into a cold, dark abyss, scattering atoms so thin they never meet again? Or will it collapse back inward, recycling everything into a fiery rebirth? The debate lingers, but either way, your atoms will follow the script, obedient to physics, indifferent yet enduring. You lean into the calm realization: impermanence is not loss, it is continuity. You are not keeping these atoms, they are only visiting, pausing here in the form of you before carrying on. They will build new stories, new lives, new worlds. You are part of their journey, not the end of it. And the humor is gentle here. Next time you shed a hair or clip a nail, you could whisper, "Good luck out there, little atom. Write me a postcard when you become part of a comet." You exhale slowly, letting the truth settle like a lullaby. You were forged by stars, carried by Earth, assembled into thought and breath. And when you're gone, your atoms will still wander, still remember their origins in fire and light, still carry the potential for futures beyond imagining. Now for the closing. The story softens, the edges blur. You're no longer drifting through supernovae or swimming in oceans. You're resting, listening to the quiet rhythm of your own breath. Every inhale is a reminder of oxygen's stellar birth. Every exhale is a promise that your atoms will one day return to the cycle. The room feels gentler now. The hum of a fan becomes the background music of the cosmos, steady and low. The darkness around you is no longer empty but full, like the interstellar dust clouds waiting patiently for their next chance to shine. You let your body sink into stillness, imagining your atoms glowing faintly, each one a lantern carrying memories of stars. They've been through fire, through collisions, through oceans of time. Tonight, they are simply resting in you, content to pause in this chapter of their journey. As your eyelids grow heavy, the thought becomes soft and comforting. You are the universe at peace with itself. Stardust curled under blankets, atoms finally exhaling after eons of restless travel. So drift now, let go, and fall into sleep. Your atoms know the way forward. They've been wandering for billions of years, and they will keep the story safe while you dream.